Alright guys, so this is still section 1.2 probability, but we're going to be doing some problems now. And this is where a lot of the learning comes from, I feel, because, well, it's just practice, you know. The more you practice, the better you get at it. And that is no different when it comes to math. So our first problem is, let's suppose the probability of A intersect B is 0.2. The probability of A is 0.6. And the probability of B is 0.5. Alright. So the first thing it asks us to do is to find the probability of A complement union B complement. So I think for me, the easiest way to do this is to draw out a Venn diagram. I think if you have a visual example or like a visual reference, it makes it easier. But so I'll draw the visual reference, but I'll also explain how to solve these using, you know, the rules from the last video, or just, yeah. So I'll draw the visual reference over here. So we have A, and we have B, and these are also, they occupy a space. Let's say, for example, you're trying to find the probability of nothing, or of everything that is not in here. Then there is a separate area that is outside of these, of this Venn diagram. And sometimes it'll ask us to find the probability of this outside area, which I think it will. Yeah, okay. So I'm looking at it will. It's going to ask us to find. You can safely assume that there will always be an area outside of the Venn diagram that you may or may not have to find the probability for. Either way, this area exists. Like, it will always be there for any Venn diagram. Sometimes it'll ask you to find it, sometimes it won't. The probability, that is. But okay, so we're trying to find the probability of A complement union B complement. So another way to read this is the probability of everything that is not in A or is not in B. So also we can go ahead and kind of fill in some of these given the information that we have. So the probability of A intersect B is 0.2, and remember that A intersect B is this middle section, so this middle section is 0.2. The probability of A, that would be the entire circle of A, which is including this middle section. Now remember, we don't want to overcount. So if we already have that the probability of this middle section is 0.2, then the probability of this other section of A would be 0.4. And that's because 0.4 plus 0.2 gives us the entire probability of A, 0.6. And you'll see later that whenever we have three circles in our Venn diagram, we can find the probabilities of section going from the inside going out, kind of like what we just did here. So again, the middle section 0.2, which means that this other section of A is 0.4. That way when we add them together, we get 0.6. And I guess just another way of doing that, 0.6 minus 0.2, 0.4. Okay? Likewise, what would this section of B be equal to? Well, if the entire probability of B is 0.5 and we subtract 0.2, that makes this 0.3. And then of course you add these together, you get the entire probability of B, which is 0.5. So we have 0.4, 0.2, 0.3. All right? If we add this together, 4, 7, 9, 0.9. That means that this outside section here, the probability is 0.1. Now if we add all of these together, we get 1, which is the entire probability space. And remember, it can't be greater than 1. It has to be equal to 1 when we add up all the probabilities. So yeah, that's what we have now. So, okay, we have filled out the entire Venn diagram with its respective probabilities. Now, it should make solving these a little bit easier. Okay, so let's go back to this. The probability of A complement union B complement. So that means that this is everything that is not in A, okay? So let's take a look at everything that is not in A. We have 0.3 right here, and we have 0.1. So that means that A complement is equal to 0.4. Now, what about B complement? Well, that's everything that's not in B, okay? We have a 0.4 here and a 0.1 here. Now, remember, we don't want to double count. We've already counted the 0.1 when we're talking about A complement. So, I mean, we'll go ahead and we'll write it in, right? So again, everything that is not in B is the 0.4 and the 0.1. And I'll actually write it like this. I'll add it together. Or I guess I'll show how we got it. And I'll do the same thing here. 0.3 plus 0.1 is 0.4. Okay. So we're up to here, right? We have this. Well, here, I'll use a different marker. This 0.3 is from this B. This 0.1 is from this outside. 0.4 from this section of A, 0.1 from the outside. And remember, we don't want to double count. So we'll get rid of one of these 0.1s. All right? So now that we have each probability only counted once, we can add these together. So 0.3 plus 0.4 plus 0.1, that gives us 0.8. So the probability of A complement union B complement is 0.8. And that was kind of just using algebra, right? And also using this visual diagram. If we wanted to use one of the rules, we could use De Morgan's law. So if you'll remember from the first video, De Morgan's law is given to us as A union B complement is equal to the probability of A complement intersect B complement. So these two things mean the exact same thing. So this is what was given to us, looking like this. But that can also be rewritten in this form. And remember that whenever we want to find the probability of something and we're given its complement, we can subtract that from 1. So what do I mean by that? So remember that A is equal to 1 minus A complement, right? Because everything else minus what is not in A is equal to A. And this was from one of the rules regarding probability. So we're given a complement here, then we can write this as 1 minus the probability of A intersect B, which is 0.2, and that gives us 0.8. So using this rule regarding, well, I guess technically we use two rules. We use De Morgan's law to find out that our problem can be rewritten in this form, and then we used a rule regarding the probabilities of complements to say that 1 minus the complement is equal to our event. Likewise, 1 minus the event is equal to the complement. It works both ways. You can do 1 minus the complement is equal to the event, or 1 minus the event is equal to the complement. It's interchangeable, which is what we did here. Also, I'm watching France-Senegal, and I hope Senegal wins. So yeah, okay. So we worked it out two different ways. One, the first way, remember, we added each individual probability, made sure that we didn't double count, and got our answer. The other way, we used De Morgan's law, as well as the rule of subtracting complement probabilities, and it gave us the exact same thing. So there's multiple ways of doing this. I personally like having this visual representation just because it's easier to see where the probabilities are coming from. Also, if you are going to use rules like I did here, then you'll definitely have to like memorize them. But it's good to have multiple ways of doing this at your disposal. Then, you know, if you can't solve it one way, you can use the other. So, okay. All right. The next part of the problem is it's asking us to find the probability of A intersect, or A complement intersect B complement. So what is the probability of everything that is not in A and is also not in B? And that's where we get 0.1. So this one was quick and easy, right? Because we already did the diagram. It's 0.1. This is everything that is not in A and is also not in B. Boom. But if we wanted to use the rules, right? I'll show you guys how to use it, how to find it using the rules. Oh my God, Senegal almost scored. They hit the post. It's the 27th minute. Okay, so to find it using the rules, what we can do first is we can actually find the reciprocal, or just the total opposite of this, right? So we will find the probability of A union B. And if you guys remember from the last video, this is equal to the probability of A plus the probability of B minus the probability of A intersect B. Sorry. Because we don't want to double count. So the entire probability of A, which is 0.6, plus the entire probability of B, which is 0.5, oh, but we've double counted this middle section, so we want to subtract one of those middle sections, so minus 0.2, and this gives us 0.9. Okay, and you know, you can also look at the diagram and see that, well, of course that's 0.9 because you're just adding these three sections together, and that gives us 0.9. All right. Now, the only way to do this would to be just to subtract 1 minus the 0.9, and then you also get the answer 0.1. And well, that's using that same complement rule where you do 1 minus everything else and it gives you the answer. So yeah, that's literally what it is. 1 minus this, which is just 1 minus 0.9, and that's 0.1. So that's how you would find that using one of the rules. But yeah, I mean, if you can draw this diagram, that's kind of all you need. But I mean, if you're quick with this, you know, do either one. Both are very useful. All right. So the next part is it's asking us to find the probability of A complement intersect B. So what is the probability of everything that is not in A and is in B? So everything that is not in A, well, that would be this 0.3 and that 0.1, because neither of those are in A. Okay, so we've got that first part done, A complement, but we're also looking at everything that is in B. So this 0.1 is not in B, so that comes out of the equation. That means the only thing we're left looking at is the 0.3, which is our answer. So the probability of everything that is not in A and is also in B is 0.3. All right. Now, let's see. Okay. Using a previous rule, if you remember that the probability of an event is the same thing as the probability of B is equal to the probability of B intersect A plus the probability of B intersect the complement of A. All right. And this is a rule from the last video. But what we want to find is this. So we'll have to rearrange this formula to make sure that we're solving for this section. And to do that, we would simply subtract this from both sides of the equal sign. Right? We're subtracting the probability of B intersect A from both sides of the equal sign. So that way we have the equation. The probability of B intersect A complement is equal to the probability of B minus the probability of B intersect A. And, well, you'll notice that those two things have already been given to us. So the probability of B, which is 0.5, minus the probability of B complement A, which can also be read A, the probability of B intersect A can also be read as the probability of A intersect B. So you can flip both events on either side of the intersect or the union, and it'd still be the same thing. So 0.2. And that gives us 0.3, which is what we said it was when we were looking over here. All right. The last and final part of this problem is the probability of A complement union B. So the probability of everything that is not in A or is not in B. So this one might be a little trickier to maybe explain, but we'll get through it. So I guess using the diagram over here, everything that is not in A. All right, so again, we're looking at this and this. All right, now we have to look at everything that is in B. So the probability of everything that is in B, which again would be this, this, and now we're looking at this middle section, 0.2. But we don't want to double count. Hopefully the camera picks it up, but I double underlined this 0.1 and this 0.3. And again, we don't want to double count, so I'll erase one of the underlines. And now what we would do is just add these three probabilities together, which gives us 0.6. And that's our answer. So again, the probability of everything that is not in A, which is 0.3 and 0.1, or everything that is in B, which is 0.3 and 0.2. I actually should not have double underlined the 0.1. That was my fault. I should have only double underlined the 0.3. So, yes. So those are the three probabilities we're looking at. We add them together, we get 0.6. Make sure you don't double count anything, and that's our answer. Now, to do this using the rules, this is where like some intuition comes into play, because we're going to use that same rule where if we have a union of events, we add one probability, add the other probability, and then subtract its intersection. But because we're looking at the complement of A, I guess maybe some people wouldn't think to do that, and I didn't whenever I was doing this problem on my own. But it works the exact same way. I guess as long as there's a union, as long as you see a union of two events, then you could do that rule. So I'll do it down here. The probability of A complement union B is equal to the probability of A complement plus the probability of B minus the probability of A complement intersect B. All right? So the probability of A complement, remember that is 1 minus A. So 1 minus A, 1 minus 0.6, so that's 0.4. The probability of B is 0.5. And then we subtract the intersection of A complement intersect B. And again, we read this as everything that is not in A and is in B. That would be the 0.3. This 0.3 is not in A, but it is in B. So we subtract 0.3. 0.4 plus 0.5 is 0.9 minus 0.3 is 0.6. And that is another way to get this answer. And that is all that this question had. Now we go on to the next one. All right. Okay, this next problem has 3 Venn diagrams, or 3 circles in the Venn diagram. So I'm gonna go ahead and draw that one. Also, it involves sports, but no, sorry, not sports. It's like a survey is made to determine the number of households having electric appliances in a certain city. So we have radios, irons, and toasters. Okay. So I'll draw the circles here. Hope that is big enough. It looks pretty big. Okay. So we'll assume, or according to the problem, the amount of households that have radios is 0.7 or 75%, but we'll do decimals. That the amount of households that have irons is 0.65, and that have toasters is 0.55. All right, so let's say that this is radios, this is irons, and this is toasters. Now, the percentage of households that have irons and radios, or I intersect R, is 0.50. The households that have radios and toasters is 0.40. The households that have irons and toasters is 0.30. And finally, the households that have all 3, R intersect I intersect T, is equal to 0.20. Now this is asking us, and this, thankfully this question only has one section. What is R union I union T? All right, so I'll go ahead and I'll fill in this Venn diagram using this information that we're given. Remember though, that if we're given something like this, it is 100 times easier to start from the middle and then work your way out. So, and you'll see why. So the innermost section of this Venn diagram would be this right here, where they all intersect, where households have all 3 appliances, radios, irons, and toasters, and that's 0.20. So you look for the section where all 3 circles intersect. Boom, 0.20. Excuse me. All right. Now we'll work our way up from this list. So this is done. The households that have irons and toasters is 0.30. Irons and toasters, that would be this section right here. Now remember, we don't want to double count, because what you see up here this middle section, irons and toasters also intersect. It's basically this entire, like, what do you call this, like concave looking thing? That entire section, which includes the middle section, is where irons and toasters overlap, which is what it's asking us, which is what this is telling us. Irons and toasters is 0.3. Now, because we've already said that this innermost section is 0.2, that means that this remaining section would be 0.1. That way, whenever you add these two together, which again is this whole section where irons and toasters inner overlap, we get 0.30. And we're going to do this for every single section. So, okay, this is done. Households that have radios and toasters is 0.4. Okay, radios up here, toasters down here. That means this section right here is what we're looking at. Now again, we don't want to double count. If we're given that that whole section is 0.40, and we already have that this middle section is 0.20, this remaining section would be 0.20. You add those two together, we get 0.40. Perfect. All right. Irons and radios is 0.50. Irons, radios, you look where they overlap, that means that that is this section right here. So again, that innermost section, 0.20, we're given that that section is 0.50, so this remaining area right here, 0.30. All right, so that's done. Now we have to find the remaining percentages of these outermost areas. So, okay, we'll start with toasters. So this section, we're given that the entire percentage of people with toasters is 0.55. And we've already calculated a couple other sections here. So I'm actually gonna get my calculator. And we can just subtract, because we're finding the entire circle now, right, of toasters. And that entire circle includes 0.10, 0.20, and 0.20. So we can take 0.55 and subtract these three sections that we've already established. That way we get this remaining section. So 0.55 minus 0.2 minus 0.2 minus 0.1, 0.05. Oops, 0.05. Now what this is telling us is that this entire circle are all the people that at least have toasters. They can have other appliances, which is what these middle sections represent. But out of the 100% of people that have appliances, then at least 0.55 of the population have toasters. And like I said, if you add all of these together, you will get 0.55. This entire circle represents 0.55 of people that have toasters. All right, irons. Again, we look at the circle representing the irons, which is this. So we can do 0.65 minus 0.10 minus 0.20 minus 0.30, and we get 0.05. So at least 0.65% of people have irons. And again, if you add all of these parts up, you will get 0.65. Same with radios. 0.75 minus, this is the radio circle, 0.75 minus 0.30 minus 0.20 minus 0.20, 0.05. All right. Perfect. Except it's not. Because remember what I said about Venn diagrams and how they exist in a much bigger sample space. So we're missing the percentage of people that don't have any of these. Okay, this looks awful, but pretend it's a rectangle. Well, it's not, but. So yeah, we still haven't considered the fact of the people that don't have a radio, an iron, or a toaster. And if you'll notice also, if we add all of these individual percentages up, 0.05 plus 0.05 plus 0.05 plus 0.30 plus 0.20 plus 0.10 plus 0.20, that very middle section, we only get 0.95. And remember that this has to be 1 for it to include the entire population of the people in this survey that the question is asking us to do. So if only 0.95% of people are within this Venn diagram, that means the people that don't have any of these appliances is 0.05. All right. Now that we have everything with its appropriate percentage, now that everything is appropriately labeled, let's look back at what the problem is asking us. What is radios, union irons, union toasters? And that's what that entire addition just proved, is that if we take everything within the circles and add it together, we get 0.95, which is the union of the people that have radios, irons, and toasters. And that's our answer. We didn't really need to find this 0.05% of people that don't have anything, but at least not for this problem. But in some problems, you might actually need to find that, you know? But because we were only finding the union of the people that have any appliance at all, we get 0.95. And you'll notice, because it's asking us to find this probability, maybe you'll remember, there's that rule where we can find this probability by adding each individual probability, subtracting their intersect, and adding the very final, very middlemost intersection. So, I mean, I'll go ahead and write it, but we already have the answer, but this is just another way of finding this, where the probability of R union I union T is equal to the probability of R plus the probability of I plus the probability of T minus the probability of R intersect I plus the probability of R intersect T. Oops. Not plus, minus. Minus R intersect I minus R intersect T minus I intersect T plus the probability of R intersect I intersect T. And fortunately, it gave us all of these probabilities to be able to do this this like summation here, or this algebra problem. But yeah, if you ever see this, if you ever see it's asking you a question and it has it in this form, what is the probability of an event union an event, you know, then you're able to do this given you have this other information. So again, this would just be 0.75 plus 0.65 plus 0.55 minus 0.5 minus 0.4 minus 0.3 plus 0.2, and you should get 0.95. Or you could do this. Either way, it gives you the same thing. All right. Okay, there's one more problem we'll do. So this one has to do with school subjects, and it's a survey of students. And it's another Venn diagram problem with 3. So we'll draw it over here. All right. So in a survey of students, it asked what their favorite subject in school was, and, or I guess what course they took, sorry. So we have that, what is it? English, math, and chemistry, right? Okay, well, the survey included 120 students, so our entire sample space is 120. And out of these 120 students, 60 of them took English, 56 took math, 42 took chemistry. Now we get into the intersection where students took multiple. So English intersect math, or students that took both English and math, is 34. Students that took math and chemistry is 20. And students that took English and chemistry is 16. And then 6 tryhards took all 3. So English intersect math intersect chemistry is 6. All right. And English, math, and chemistry. So now we can start filling this Venn diagram in. So we have 6 that took all 3. So that takes the place of our innermost section right here. 16 took English and chemistry. So English, chemistry, that is this section right here. And remember to find this non-labeled section. 16 minus 6, that's 10, so 10 goes there. math and chemistry, that is this right here. We already have 6. 20 minus 6 is 14. 14 goes there. English and math is 34. English, math, right here. So 34 minus 6 is 28. 28 goes there. Now, 42 students took at least chemistry. So we look at the chemistry circle of our Venn diagram right here. And we do 42 minus 10 minus 6 minus 14. So this remaining section of our chemistry circle is 12. At least 56 students at least took math. So we do 56 minus 28 minus 6 for the middle section minus 14, 8. And that goes right here. All right. For English, 60 students at least took English. So 60 minus 28 minus 6 minus 10. So 16 goes right here. And again, this lets us know that if we add each individual piece of math, for example, 8 plus 14 plus 6 plus 28, we will get 56. Same for chemistry, same for English. Okay, what about the students that didn't take any of them? And actually, that is the first part of this problem, is how many students took none. So we have to remember that we have that part of the sample space where it's possible no students took any of these. So what we can do here is we add each individual section up, get a total, and then subtract that from our entire sample space, which is 120. So 16 plus 12 plus 8 plus 14 plus 28 plus 10 plus 6, 94. 120 minus 94, 26. That means 26 students did not take any subject, and that goes right out there. So again, we added up each individual piece, got a sum total of students that at least took a subject, and then subtracted that from the total number of students that were interviewed to get 26. 120 minus 94 is 26. And if you wanted to use the rule, then remember that what you can do is find the probability of the union of all of this. So that looks like the previous example we did, where it's the probability of E plus the probability of M plus the probability of C minus these intersections here, and you add the final intersection where they all intersect. So that's just, P of E. I won't write out P of E plus P of M. I'll write out the numbers instead. So 60 plus the probability of math, 56, plus the probability of chemistry, 42, minus the probability of English intersect math, which is 34, minus the probability of math intersect chemistry, which is 20, minus the probability of English intersect chemistry, which is 16, plus the probability of English intersect math intersect chemistry, which is 6, and that will equal 94. 94 students at least took a subject. How many took none? 120 total students, minus the 94 that took something, 26. All right. The next question is, how many students took math but not English or chemistry? And this one very obviously is 8. How many students took math? So we look at the math circle, which is all of this, but did not take English or chemistry. So right here is where math and English intersect. So we cannot count either of these two sections. All right? So we have 56 total students that took math, minus 28 minus 6, 22, or did not take chemistry. So we look at the chemistry section right here, which is 6 and 14. Now we've already subtracted 6 once, we don't need to do it again. So we have 22 remaining students, minus 14, which is 8. And remember, we got that 8 from counting from the inside out. So, now that we already have a number here, we can just look at the question and be like, oh, well, it's that. Because 8 students took math that also did not take English or chemistry. So 8. Now, how many students took English and math but not chemistry? So we have to find the section of students that took English and they took math, but they also did not take chemistry. And if you wanted to write out in P the probability of form, so English and math, which means they intersect, English and math intersect, and did not take chemistry, so the complement of chemistry. So intersect because it's the students that took English and math and did not take chemistry. So that's what that looks like. E intersect M intersect complement of C. Okay, so let's look for the part where English and math intersect. Okay, right here. English, math, this right here. That's where they intersect. But we're also looking for the students that also did not take chemistry. This 6 represents where all 3 subjects intersect. But if we're counting the students that did not take chemistry, we can't include that 6 in our answer. So let's just kind of put an X over it. That means we're left with 28. So it's 28. The probability of students that took English and math and did not take chemistry is 28. Okay, this is the end of chapter 1. Thank you.